last. We began our study of Euclid's elements. Euclid's elements. We discussed the various, let's go to book one. In particular, we're going to book one. Book one. We talked about the 23 definitions, which again are problematic. The postulates, the 5 postulates, P1 through P5. P1 through P5. P5 being the most mouthy, being an entire paragraph and controversial. Common notion, yes?
I started working with the first problem and a little bit of the second problem.
Yes.
And I felt like when I was doing the proofs, I was having to check, like if statements I was making were postulates that had already been proven
Yes.
before the one that I was proving.
Yes.
And in order to do that, I had to like know the numbers and the order, I guess.
Yes.
So like on an exam or quiz, like how would we then demonstrate that? Because I know you don't want us to like memorize the number and the orders and exactly.
You can't memorize it.
Yeah.
I mean, you could, but yeah, that's not what I'm asking. I would give you every fact that you're allowed to use in your proof.
Okay.
Because we have this issue where theorems use facts that require other facts, you know, you would have to reconstruct the entire element. If I ask you to prove I-23, you'd have to say, here are the definitions, here are the postulates, here are the first 21 propositions that then prove, or 22 that then prove I-23. So that's not reasonable. I would have to give you every fact that you need in order to prove the statement that that you're trying to prove. Okay. So I'd have to give you all the tools. Does that make sense? Other questions? Okay. So we talked about the 5 postulates. We didn't spend too much time on the common notions, but the common notions are things like, oh, maybe we did actually, things that are equal. If A equals B and B equals C, then A equals C, that kind of thing. These are common notions. The whole is greater than the part. If you have one line segment that sits inside another line segment, then the one that sits inside is less than the longer one. Okay, things which coincide, like, yeah, common notions, right? Things we can take for granted. Okay, proposition 1, to construct an equilateral triangle on a given finite straight line. So let's get this down. We would spend the entire semester if we did Euclid's elements properly, proposition by proposition. It's an outstanding exercise for logical thinking. Maybe we'll talk about Plato a little later, but Plato's Academy, you know, had this sign overhead, let no one ignorant of mathematics enter here. This kind of study, the reason you guys are learning this, I think, is because it will make the kind of brain workout that studying this stuff gives you will make all your other classes and life in general easier, right? You will have the capacity to work on those things. So, okay, so we're not going to do Euclid's elements comprehensively. I strongly recommend it. I think it's an outstanding exercise. You have all the tools at your disposal. We're just going to touch a couple of things. I do want to touch proposition 1. So let's talk about proposition 1, and you'll see in a second why. Proposition 1 is to construct an equilateral triangle on a segment. Okay, so let's do this. Like, did you guys have these 2-column proofs in high school? You were subjected to that. Okay, so column 1 is the statement. Remember, this is very similar to what we talked about when we first discussed Talus and the fact that people realize you need not just a statement of what's true, but a why. So there's like a what and then a why. Okay, so I should have left myself a little bit of room for a picture. Okay, so yeah, here's a picture. Here's our little segment A and B. There's a what and a why. Okay, so we're given A and B and the line segment between them. Why are we given? Why is that? This is like step 0. This is assumption. Everybody's happy with that. Step 1. What does Euclid say? How are we going to construct an equilateral triangle? Draw a circle. Yep, let's draw a circle with center A and radius. Well, there's only one other thing happening here, which is the point B. So we'll draw a circle centered at A with radius AB. Why can we do that? Exactly. There's a postulate that says we can draw a circle given a center and a radius. That's postulate 3. Okay, so Y is P3. Step 2, draw a circle with center B. Oh, what is the, I gave it away. What is step 2? Draw a circle with center B, thank you, and radius AB. Okay, so do the same thing on the other side. Why are we allowed to do that? P3, postulate 3 allows us to draw circles given a center and radius. Okay, let's call C this point of intersection. Let C be the intersection. Then what we want to do is draw AC. Why are we allowed to draw AC? Yep, postulate 1, construct a line between any 2 points. So this is postulate 1. Then we're going to draw BC. Step 5 is draw BC. That's also postulate 1, allows us to draw BC. And now we want to argue what we want is an equilateral triangle. The claim, so we're done with the construction, but the claim is that this triangle ABC is indeed isosceles, not just isosceles, equilateral. So we have to show that all 3 sides are equal. So we know that AB is equal to AC. That's because they're both radii of that first circle. Both radii. Radii of circle. Let's give these circles names. C1, C2. So C1 is the first circle we drew. C2 is the second circle. They're both radii of C1. And what about AB versus BC? Bless you. AB is equal to BC because they're both radii of C2, right? AB is a radius of C2. BC is also a radius of C2. Radii are equal. So these are both radii of C2. And Y is AC. And AC is equal to BC. Y is AC equal to BC. We have 3 equalities. Every pair of sides. What it means to be equilateral is that every pair of sides is equal. So we know that side AB is equal to AC. We know that side AB is equal to BC. Why is AC equal to BC? Yes, the transitive property, which is common notion 1. Things that are both equal to the same thing are equal to one another. Laurie.
We need to explain it like this in an exam and not just say that all the radius at the same circle.
We'll be much more, I'm trying to be extremely precise at this moment. I'll choose things that don't go down to this level of really, do I have to say that? Yeah, I'll make sure that that what you're asked isn't this tedious. But here we really, really want to be very precise. This is common notion 1. Common notion 1 is that things that are equal to the same thing are equal to one another. Okay, and if you look at proposition 1, look at what he does. Okay, he constructs, just to show you that what we did is exactly, bless you, what he did. Euclid says you're given AB. We want to construct an equilateral triangle. You describe this circle, you describe that circle. You use postulate 3, you use postulate 1 to draw the lengths. Because definition 15 is that what it means to be a circle is that all the points are equidistant to the center. I didn't mention that, but that's what I say. They're both radii. This is definition 15, I-15, is what says this.
And then finally, so we have that AC and BC are both equal to AB, and two things that are equal to the same thing are also equal to the other. That's common notion one. Therefore, all three straight lines are equal to one another, and we've constructed an equilateral triangle. Definition 20 says what it means to be an equilateral triangle. It's that all sides are pairwise equal. Okay, and therefore, by definition, what was it, 20 or something? 20 is satisfied. Okay. Quod erat demonstratum? Question. Definition 20, you mean? Definition 20 is what it means to be. So let's look at it. What is definition 20? It says of trilateral figures, in other words, in a triangle, the equilateral triangle is the one that has three sides equal. So what does it mean the three sides are equal? It's that any pair of sides is equal. So we've shown that this pair of sides is equal. We've also shown that that pair of sides is equal. We have to show that this last pair of sides is equal, but that's because of this transitive property of equality, the common notion one. Okay, very simple. We're off to, like I said, a very simple start in this book that aims to give a perfect, completely logical, from first principles, from the axiomatic treatment of geometry. We're going to build up all kinds of stuff. There's a glaring hole in this argument, a massive gap. The very, very first proposition that Euclid proves in book one, proposition one, is just wrong. It's not that the statement's wrong, it's that the proof is wrong. And there's an absolutely massive hole here, which it's very difficult to see. But the second you see the hole, you can't believe that you didn't see the hole. Where's the hole? The hole is staring you in the face. You get the prize. Right here. Right there. There's a gap, a blatant hole, a gap that says let C be the intersection. Which axiom says that C exists? Here's a circle, and here's another circle. Let C be their intersection.
It's not enough that we just have two circles that are clearly overlapping.
We are supposed to use, look at how careful he was with everything else that he did. Even when he was done proving that AB is equal to AC and AB is equal to BC, he took the extra step to say, yes, therefore AC is equal to BC because of common notion one. He really wants algebra to be words. He wants everything to be like proved from first principles. What is the principle that says C exists? He doesn't give one. He relies, Layla?
Would it not work with the definition of what a point is? Can you use a definition instead of a?
Well, he should give a definition. What he's missing is a postulate for when circles intersect. What are the conditions under which it's not true that any pair of circles intersect. You can have two circles that are completely disjoint. You could have maybe two circles where one is inside the other. Well, that's a horrible picture, but you know what I mean. When is there an intersection point? Completely misses this. He draws the picture. It's obvious to everyone what he means. That's exactly what he's trying to do, is not to make things obvious. He's like explicitly spelling out things that to us are blatantly obvious, bless you. And yet here, until you see it, you can't see that there's anything wrong. And the second I point out that there was no entry in this column, it's not clear what's going on. And once you see it, you're like, oh yeah, how did we miss that? Right? We're being so pedantic about everything that's going on, and yet he just misses this.
It's nothing that elements that say if there are two shapes and they touch each other, that is an like there's no definition of an intersection.
When do you know the two shapes touch? All kinds of other things that he does, he's extremely careful. And you'll see as we go further in, he's extremely careful about everything. He just screws this up. And it's the first thing that he does. Anna.
Is something's gonna go at the very beginning of the process, but
why is it not acceptable for like that to be just like an assumption that you make?
You want to assume that the two circles you've created intersect. You can do that, but that adds an extra hypothesis to the proposition. The proposition would be to construct an equilateral triangle on a segment, assuming that the two circles that you construct on the ends will intersect. Well, you don't want to do that. It's mathematics is an art, and we're seeing the art form play out before us. And it's like a piece of music where there's parallel fits in a Bach chorale, and you're like, well, that doesn't sound good. Of course, modern music is full of parallel fits, if you know what that means. But to Bach, that would be like, that's not nice. In the same way, you want this to be clean, and it's so clean everywhere else, except right at the beginning. The very first thing he does, he like just blows right through this issue, having been so careful about everything else.
So the
Alicia.
intersections, basically, you just didn't specify that the circles were supposed to intersect.
Yeah.
That's it.
Which axiom, axiom, proposition, theorem, common notion, what says when circles intersect? They certainly don't in general. Why do these two intersect? We can see with our eyes that they do. Our eyes are what's so hard to divorce us from the logic. Lori.
Radius. They have like a point, which is the radius of both of them. So
Go on. So what is the exact condition under which those any pair of circles, I give you a pair of circles, you're saying that what it takes for two circles to intersect is for them to share a radius?
they're also that one of them is like real.
He didn't specify any. In fact, later on, maybe I should have added, okay, it's too late. I already gave you your homework, but there's a, I forget which proposition it is. He says to construct the triangle given lengths. So he constructs, you're given, which one is it? If I can find it immediately, I will. To draw a triangle given two lengths. To construct a triangle out of three straight lines. Okay, so proposition, this is not where I had in mind to go, but let's just jump here for a second. You're given three straight lines. Here's one straight line. Here's another straight line. And here's a third. And he says you can assemble those three straight lines into a triangle. Okay, how do you do it? We're about to, I'm a little going out of order. You're allowed to move lengths. So what he does is, so let's say this is length, I'll just give these names, AB, CD, EF. Okay, given this, make a triangle. Okay, so he says you have E and F over here. What you'll do is you'll measure the length of CD with your non-collapsing compass. This is the next thing I want to discuss, is a collapsible compass. You'll measure this length CD and you'll draw a circle here whose radius, this radius is equal to CD. And then you'll go over here and you'll take the length AB and you'll draw a circle here whose radius, this radius is AB. And then here's your triangle. There's a problem with this.
Measure the length of its intersection.
I'm skipping. I should have first given you I2. I2 is what allows what I'm doing right now. You can pretend that we're going to come back to that in like literally 10 seconds. Okay. So he does this construction, but he doesn't do it in a naive way. He says to construct a triangle out of three straight lines, which equal three given straight lines, meaning line segments. It is necessary, in order to do this, it is necessary that the sum of any two of the straight lines should be greater than the remaining one. There's something called the triangle inequality, which is that if you want to go from E to F, the distance from E to F cannot be more than the distance from E to G plus G to F. That's something that he proves. So he says here, in order for this, in practice, what he's saying is in order for these circles to intersect, he's giving you the condition under which two circles will intersect. It's that the radius of one and the radius of the other and the distance between the two radii satisfy the triangle inequality in all possible ways. So it's sitting right there. What he needs is sitting right there at I-22. He needed it in I-1, and he needed it as an axiom in order to be able to do anything. Okay, but so as massively amazing this document is, it is still fallible. You know, we should. It's very easy to stand here 2,300 years later and judge Euclid and say, you know, by modern standards, whatever. By his own standards, I would consider this I-1 a mistake. Layla.
So I-22 would solve this issue of circles intersecting?
Yes. It's I-22 is getting to the heart of the issue of what appears in I-1.
Because it allows you to measure a radius? It's not.
Well, it's not that it's allowing you to, so again, you have a line segment that he calls the segment A, he calls this segment B, he calls this segment C. Okay, so you start with, I guess he starts with B, and then he moves the length A to DF, then he moves the length C to GH, and then he draws one circle, the green circle, with center G and radius H. He draws another circle with center F and radius D, just like we did. And then why do the two circles intersect? I say, where did he say letter K? Describe the circle DKL with center F, and again, join KF and KG. Even here, he's hit on the thing that he needs, but he screws this up. It's not perfect. We're looking at a beautiful symphony and pointing out an instance where there's perfect parallel fifth motion. Like, let's, you know, everything with a grain of salt. Okay. Oh,
I don't understand what I-22 has to do with the intersection of two circles.
yeah. So if I draw you two circles, so here's the real question. Question that was omitted and is implicitly answered in I-22 is, when does a pair of circles actually intersect? Okay, so to answer that question, think about what it would take for a pair of circles to intersect. So here's one circle, and I want to draw a second circle, and I want to ensure that they intersect. If the circles do indeed intersect, then that creates a triangle, some kind of triangle. And in a triangle, there's always the triangle inequality. The triangle inequality, which he proves, where's the triangle inequality? If the ends on the side of the triangle, the sum of the two straight lines so constructed is less than the sum of the remaining two sides. So I-21, see, the beautiful construction is I-21 proves the triangle sum of any two sides greater. Okay, sorry. I-20, I guess, is in any triangle, the sum of any two sides is greater than the remaining one. I-20 is the is I-20. The sum of any two sides is greater than the third. Right? That means that's the same thing as saying, if you want to travel from this point to this point, you are not better off by going in the middle, by going somewhere else instead of going straight. Right? The sum of these two lengths is going to be more than if you just went by the straight line. So this triangle inequality is the key notion that you need in order to be able to properly state the conditions under which two circles intersect. That's all I wanted to point out here. Is that yes, it can be answered. It can be answered exactly by his tools, and he screws this up. Sorry. Okay, I2. Let me tell you what I2 is. So I1 is constructing an equilateral triangle. I2 is, and this is how we know that the compass in Euclid's mind is a collapsing compass. The second you lift it up off the ground, it falls apart. So I2 is that you can pretend it doesn't, that the collapsing compass is just as good as a compass that can be locked. I'll write it that way in lay terms, and then we'll see the I2 says the Euclidean compass is collapsing. But we can pretend that it locks in place. Okay, so that's the interpretation of what it says. What it really says is, given a point and a segment somewhere else, you can move the segment to the point. Okay, so more precisely, so if I'm given, if I have a point A and I have a segment BC, so given A and a segment BC, I can construct some point D somewhere, and construct D so that AD is equal to BC, so that these two things are equal. Even though I have a collapsing compass. Anna. Oh, I'm sorry. This is annoying. Is that better? You want a minute to think about how you do it? Lori.
It's quite possible, isn't it, to solve the whole in the trisecting an angle? Without having to.
So the trisecting an angle problem is that you lock your compass and then you measure it on the segment. So what you're not allowed to do is take the compass, put it on the line segment, and simultaneously manipulate both the compass and the segment. Or at least there's no axiom that allows you to do that. Okay. What this says is you can move a length to a given point. The problem with the trisection is you don't know where you want to move it yet. You have to figure out where you want to move it by wiggling around the segment. Well, this is okay. So let me show you. Where's GeoGebra? You see, they have two tools for circles. One circle is a circle with a center and a point. You give me a center, you give me a point. That's literally what a compass does. They have another tool, which is that if I have a segment and I have a point, there's a segment, there's a point. This is a tool that says I can choose a segment for the radius, and I can move that segment to E. That tool does not really exist. That's like locking your compass on DC and then just putting your corner at E and drawing that circle. You can't do that with Euclid's compass. Otherwise, he wouldn't need I.2. The whole point of I.2 is, even though your compass is collapsing, the second I lift my compass off of DC, I lose the length. We can pretend that it's not. We can act as if it's not. Okay, we can, even with a collapsing compass, do the same moves that a locked compass would accomplish. Okay, so GeoGebra allows this tool, even though it's not really a proper Euclidean tool, just like it allows bisection. Bisection's not a tool, but it's something you can do with construction. So you may as well. It allows you to use these tools as subroutines. Right? Anything that you've already constructed, there's a subroutine for constructing midpoints. Just go ahead and give me the midpoint. Don't worry about doing it from scratch every time. Okay, you want a minute to think about how you do it? Take a minute. Take a minute, talk to your neighbor. How would you, without lifting anything off the page, how would you use circles and straight lines to construct this point D? Take a minute.
You put one number and three and one number and three and then lock.
Okay. So we have and then we just want.
We make a circle.
So I'll go. We have a circle B.
Just the proposition one.
Shall we do it together? You see, it looks like something so simple. But then if you actually have to come up with it yourself, you're like, wait, how would you actually do this?
Shall we do a 2-column again? All right, here's the what, and the why. Okay, so we're given a point A and a line segment BC. We're given, this is step 0. We're given A and BC. Why? Well, that's the assumption. Step 1. Draw the line segment AB. Is that what you're going to say? Okay. Draw AB. How come we're allowed to draw AB? Yeah, it's P1. The first postulate is that you can use a straight edge. Step 2. Remember I said that you want to use previous postulates or now propositions, since we're on proposition 2. We want to use propositions as black boxes, as subroutines. So construct an equilateral triangle on AB. Make equilateral triangle, let's call it ABD, all but dissertation, on AB. Why are we allowed to do that? I1, we just proved it. We just proved that you can construct an equilateral triangle. This is the same as this is the same as this. This is not the same, right? BC is just some other length. I hope you guys will enjoy this. This is very clever. Next, we're going to draw a circle centered at B with radius BC. Draw a circle with center B and radius BC. Why are we allowed to do that? Yeah, you can flip back. Which proposition? Not proposition. Postulate. Postulate 3. P3. Yes, exactly. P3. Okay, I'm going to draw this circle. I wouldn't yet know where he's going with this if I didn't already know this proof. Step 4, extend dB until, well, here we're going to get a little sloppy again, but we're going to, until it hits, let's give this circle a name, C1. Here's a circle C1, until it hits C1. Again, what are the conditions under which a circle is hit by a line? We have to be more precise with that, but never mind. So until it hits C1 at E. Why are we allowed to extend a length? A length that we already have? Because you can produce a finite straight line continuously in a straight line. You can extend a length that you already have. Okay, that's P2. Now what? Does anyone see what he's done? If this length that we want to move is x, and this equilateral triangle is y, then he's created the length x plus y over here. Amelia, you see it? Yes, exactly. Exactly. Can you still see it at this? Yeah. Exactly right. So now you see it. Draw a circle. We'll call this the Amelia circle. Centered at D and radius DE. Okay, so it's going to be like that. Big circle. Why are you allowed to draw that circle? Postulate 3. Yeah, you're going to get to know these postulates by name. Oh yeah, P3 does this, I27 does that. Not really. We're not going to spend enough time in it to really get that far. Okay, why did you say to do that, Amelia? Yes. Exactly right. Exactly right. Let's call that new point F. Extend dA to F on, this is circle 2. This is circle 2. C2. Why are we allowed to extend a segment a little farther than it was originally drawn? P2. Awesome. Okay. And what is the length of DF? So we're done with the construction. We're done with the construction. The proof I can put over here. The length of DF is equal to x plus y, except that's not how Euclid would say it, but let's just skip ahead. It's x plus y. And so the length of AF is, everybody see? This length is y. The total length is x plus y. So AF is x. Is x. So F is the point that we wanted. F is the point. The desired point. Desired point. Cool. You do not need a collapsing, you do not need a locking compass. You can accomplish everything you want with a compass that is collapsing. It'll work just as well as one that doesn't collapse. Does that make sense? Should I draw this in GeoGebra? Will it help you to see it in the real? Okay, I'm seeing yeses. So we've created a point F that with AF equal to BC. Maybe I called it something else up here. I called it D, but I just want to construct, I want to move the length BC over to A. And I've done that, and that length is AF. It does equal EB. Yeah, but EB is not at A. I want to move the length BC to A. How do I get it there? I can't just measure my compass, lock it, and place it there, but the world is as if I could. Okay. Do we need to see it in GeoGebra? It takes 10 seconds. Yeah, let's see it in GeoGebra. Okay. So we're given
Also switch it up when you see the something else. Like when you wrote it out.
You mean the name?
Because I feel like I'm getting lost because it's like make AD the same as BC, but then there's like it's not, it's AF.
Sure. You mean over here? Construct a point F so that AF is equal to BC. Is that better? Okay, great. Mathematicians are what's the word? Like, we don't remember names of things. We're name agnostic or face blind or something. I don't know. Anyway, okay. So we're supposed to draw a regular triangle let's draw a regular triangle. So what do? I select 2 points, and then I enter the number of vertices. I want 3 vertices. That will give me a regular triangle. Why am I allowed to draw a regular triangle? Exactly. I1. Yeah, exactly. Exactly right. Now I'm going to draw the circle, the only kind that I'm allowed, given a point and a center, from B to C. Now I'm going to extend DB. So extend means I'm going to draw a ray, for example, or an entire line from D to B. You see, I've extended it. Why do they intersect? Okay, Euclid doesn't quite get this so right, but they do intersect, as we can all see, and they intersect at this point, E. Then we again make a circle from D to E, and we extend DA by a ray. This is postulate 2, and we get this new point F. And if we measure, where's that measuring tool? Distance? Yeah, distance. If we measure AF, that's 2.76. And if we measure BC, that's also 2.76. We've moved the length of BC to the point A. Everybody see that? And if you wanted to put it somewhere else, not at F, but at some other point, well, okay, you just make the set of all points that have that same distance from A as the length of BC is the circle. So now you can put it wherever you like. So here's a totally arbitrary point that has the same distance to A as BC. Does that make sense? We're happy with that? Okay, so that's what I2 is trying to accomplish. We're not going to go through, like I said, we're not going to go through these various propositions one by one. There's I1, I2. You can make isosceles. If you have isosceles triangles with base angles, in an isosceles triangle, the base angles are equal. This is a very interesting proposition. I encourage you to read. Dunham has a nice description of what goes wrong there. I11 is in a straight line at right angles to a given straight, to draw a straight line at right angles to a given straight line. That's to drop a perpendicular. Is I11. I14 is in a straight line and a point to it. 2 lines not adjacent angles equal to 2 right angles, then the 2 lines are never mind. Some of the I'll come back to the ones that I need. I really encourage you, if you have the time and interest, to go through this in some detail and try to read them. It's hard to read some of these, and then you click on the button and it'll have a picture, and then you'll say, oh, okay. Actually, is this one on your homework? I think it is. Okay, so let's not go over it. I think this one's on your homework. If you have 2 parallel lines, no, if you have a straight line falling on 2 straight lines so that the alternate angles are equal to one another, then the straight lines are parallel. They cannot intersect. If they do intersect, you come up with a contradiction. Okay, this is I27, and it's the last proposition that does not use the parallel postulate. I28 is the first time the parallel postulate is actually used. So the first 27 theorems in book 1 are just as valid in spherical geometry on the surface of a sphere, just as valid in hyperbolic geometry, which we haven't discussed, but we will. Laurie. The parallel, this is real. Okay, so let's talk about this just for a second. The parallel postulate is saying something that's like the converse. The parallel postulate is a definition, which is the converse to I27. So I27 says if you have 2 lines and a transverse line with opposite angles equal, then the lines are parallel. Lines are parallel. Okay, they do not intersect in the plane. If they did, you'd come up with a contradiction. It's your homework to figure out why. That's like the if you look at I28 is if a straight line falling on 2 straight lines makes the interior angle equal to the interior and opposite angles on the same side. Bless you. The sum of the interior angles on the is equal to 2 right angles, then the straight lines are parallel to one another. So this is saying makes the exterior angle equal to the interior angle and opposite angle on the same side, or the sum of the interior angles on the same side are equal to two right angles. Okay, this is saying that if let's remember what P5 says. P5 says if the two lines, if 1 and 2, if angle 1 plus angle 2 is less than two right angles, then the lines cross, the lines intersect. Okay, so yeah, so it's like a converse. It's like a converse. Let's skip ahead to, because I'm hoping we can get to the Pythagorean theorem today. Let's skip ahead to 46. 46, as I said, 47 is the Pythagorean theorem. 46 is to describe a square. Let's go over that one, because that's a good one and an important one. So I-46. Proposition I-46. Remember, we start with, here's an equilateral triangle. Now we're going to construct an equilateral four-sided chain. To construct is the way that he would say it. It's like a, what's it called? The verb that's a verb that's in action. Why am I blanking on? Definitive. Infinitive. To construct. Well, this is to construct, yeah. But it's like go. Imperative. Okay. You'll see my lack of education. To construct a square, a regular quadrilateral on a given segment. On a given segment. So we're given. So let's do the what and the why. And we're given AB. Give 0. We're given A and B and AB, Y assumption. And our goal is to construct a square. Okay. Step 1, let's look over what Euclid does. So step 1, given AB, I'll try to follow his diagram. Draw AC at right angle to AB. So drop a perpendicular at A. Make AC perpendicular to AB at A. Okay, so drop a perpendicular here. And let's just call this point C. Why am I allowed to do that? Where can we drop, where a perpendicular is made? I-11. I-11 is where he shows how to drop a perpendicular. Okay. So trust me, we can make a perpendicular, or don't trust me, but we can. Step 2 is we're going to make a length on A that's the same as the length AB. Now here's something funny. He could just say, draw the circle between A and B and mark this point D. So this is let D on AC have length to A the same as A to B. I would do this by drawing a circle and arguing that this length is the same as that length. What Euclid uses instead is I3, which says you can move a length to a point in a particular direction, which is one more step than you can move a length to a point, right? So this is I3 or I2. Yeah, I may as well be a little bit more precise. It's I3. But you saw how you can move lengths by I2. I3 is the next step after I2. Okay. Then, sorry?
Draw a circle with radius AB, center A, and wherever it is C.
That's what I would do. Euclid decides he's going to use something more powerful. I3 lets him do it without needing to argue after drawing the circle that I3 is like, yeah, anyway, it's overkill, I would say, to use I3 here. I agree with you. I agree with you completely. Just draw the circle and argue that that both lengths are radii. But all right, he uses I3. Next step, this is where it gets interesting. draw DE parallel to AB. So draw DE parallel to AB. Why are we allowed to draw parallel lines? That's because of I-31. I-31 says draw a straight line through a given point parallel to a straight line. Okay, so we're in the back half of the book where we're using the parallel postulate. Of course, that's only possible. This is what did I say, 31? 31. I-31 says I can draw a parallel line. So let's call this point E, and line DE is parallel to line AB. Okay. Everybody with me so far? Then what? Then he says, draw. I would argue that he should separate this E from that E. Draw BE through the point B parallel to AD. I'm going to say it slightly more precisely. Draw BF parallel to AB at B. So drop another parallel over here, and this point I'll call F. So this line is parallel to that line. Sorry, parallel to AC or AD, doesn't matter. Not AB, AD. And again, this is I-31. Okay, does it make sense? So once we've drawn one right angle, then we draw a parallel line to DE and a parallel line to BF. Okay. Then there's a theorem. So we've done the construction. Okay, and let's give their intersection a name. 5. Again, we have to argue, why does this intersection exist? Let G be the intersection, bless you, of BF and DE. BF intersecting DE needs explanation of why this intersection exists. Why can't these lines be parallel? But never mind, we'll just draw that point G. And of course, the claim is that ABGD is a square. We need two things for a square. All sides are the same, all angles are the same. So we need to know that BG is the same length as AB, is the same as AD, is the same as DG. We also need to know that these are all right angles. Nargis.
Postulate 14, that it's like if there's a line that intersects parallels, then the angles are right.
It's a little subtle. It's a little subtle, but that's pretty close to that. So the first thing that he says is in his diagram, I guess I've gone off he has this point E doing a little too much work for my taste. I would separate it into E and F, and then G is the point. He says, first of all, so the proof of this, why is that what we want? He claims, first of all, that ABGD is a parallelogram. Right? It's got two sides that are parallel and two other sides that are also parallel. That's a parallelogram. So in any parallelogram, if I have any parallelogram where these two sides are the same and these two sides are the same, I tried to draw it so that it was not equilateral, but I kind of failed. It's a parallelogram by construction. And in a parallelogram, the lengths of the opposite sides are equal. So length 1 is equal to length 1, and length 2 is equal to length 2. That's called I-29. I-29 is that opposite sides in a parallelogram are equal. Parallelogram are equal. Okay, so the opposite side from AD is BG, and the opposite side from AB is DG. So the opposite side, I'll just write it here. AB is opposite to DG, and AD is opposite from BG. Okay, so far so good. So now we've shown that all four sides are the same. And of course, AB and AD by construction are the same. And these two are equal by construction. So now everybody's equal. Why are the angles right? So what he says, next I say it is also right angled. Since the straight line AD falls upon two different parallels. So there's oh, is I-29 the wrong thing? Did I mean I-34? Maybe I meant, this might be I-34. Whatever, that's not important. Let's look at the argument. The argument is if you have parallels, remember this thing that we were just talking about? If you have parallel lines, then the opposite angles are equal. This angle is equal to that angle. That's I-30, I-31, I-29, I-29. I-29 is that if you have two parallel lines, then opposite angles are equal. And so he says, look here, these two lines are parallel. DE is parallel to AB. This angle is opposite this angle. Everybody see that these two angles are opposite? And therefore, this is a right angle. Similarly, because this is a right angle and these two lines are parallel, this angle and this angle are opposite. And what you'll see in your homework is that vertical angles are opposite. So this angle is opposite. This angle is also a right angle. And then these two lines are parallel. Therefore, this and this are opposite. So that's how he establishes. I'm not going to write all that down. It's not, you see hopefully what I'm talking about. So he gets to the right angles by chasing around. So now chase angles. I'll just say it in words. Now chase angles across different pairs of parallel lines to show that all angles are right. Quod erat demonstrare. So here's my question to you. Isn't there a simpler construction of the square? And don't we already know a simpler construction of the square? And why does he rely on parallel lines? Once he's moved from A to D with a right angle and a circle, why doesn't he just move from over here with a right angle and a circle, and then over here with a right angle? Isn't that what we would do? Isn't that how everyone? So question, isn't the following a better construction? And doesn't it not rely on drawing parallels and the parallel postulate? So here's the construction. It's exactly what we have been doing all along. You're given AB, draw a perpendicular, AD equal to AB. So exactly as we just did, okay? I get the point D. Just do it again. Draw a perpendicular, D, what was that letter? G or something? G? I know you guys don't like it when I switch letters, so I'm going to try to keep the letters the same. DG equal to AD. Okay, draw that perpendicular, drop a perpendicular and make it the same length as G. Okay, I can drop a perpendicular to AD. I can draw that circle to make it the same length as AD, which is also the same as AB. And then just draw BG. Draw BG. And then you're done. We didn't need the parallel postulate. Why is he doing all this? Layla, please.
So if you draw the parallels,
Yes.
you will able to know the length because Euclid says that you're able to maintain a length, right?
Because of I-34 about parallelograms. We can go into the proof of that if you like. The proof of I-34, so this is a little aside. I-34, if it is what I think it is, you have, let me try to really make it not equal, not an equilateral parallelogram. You have a parallelogram, and your claim is that, in fact, so let's give this these things names. So A, B, C, D. So we're given A, B, C, D, a parallelogram, and the claim is that opposite lengths are equal. AB is equal to DC, and AD is equal to, I wrote DC, but I said BC, or maybe I said the right thing. Anyway, you know what I mean. The opposite lengths are equal. Why is this true? The proof is because they're parallel, we're going to draw a diagonal, AC. We're allowed to draw, you don't need me to do these things. Because they're parallel, this angle is equal to that angle. And this length is in common. This length is common to both. And so you're going to use side angle side. You're going to use side angle side to show, just show then. I'm skipping a lot of steps. It's very to do this really precisely, as you saw, takes some effort. But the triangle ACD is in fact congruent to the triangle CAB, where I'm careful about the order. So AC is the same as AC, AD is the same as CB, AD is the same as CB, and CD is the same as AB. CD is the same as AB. Okay, because they have this common thing, and these two lines are parallel. This line crosses a pair of parallels, but this line also crosses a pair of parallels. In fact, it's maybe even easier. Anyway, this angle is equal to this angle, which is equal to that angle. You have to do a little bit of diagram chasing to show that that you have three angles that are equal and one side that they have in common. So from that, you can conclude that they have equal opposite sides. Does that give a hint to what's going on? So because this square was constructed first as a parallelogram, first and foremost as a parallelogram, he concludes that the opposite lengths are equal. And the two of the adjacent lengths were equal by construction. Therefore, all the lengths are right. So I come back to this question. Why does he bother using parallels at all? Seems like a harder construction than this one. And this one doesn't use parallels, Laurie.
Because he needs that as the setup for the next one.
It's true that he's proving I-46 because that's setting up for I-47, which is the Pythagorean theorem. But why couldn't this have come way earlier? You know this thing I said done. You can hide a lot of stuff in a little word. Yeah, how do you actually finish it? How do you actually prove it? Correct. And that the last length is the same as the others. It's not even true without assuming the parallel postulate. Okay, so this question, or the answer to the question, is it's not true without using parallel lines, unless we use E5. What's the example? What's our favorite example of a geometry where something goes drastically different? What is it? The sphere, you mean, the geometry that we live on. Is that what you're trying to say? No. What were you saying? Yeah. Okay, maybe I gave it away. Look on the sphere. Look at the first four, maybe I didn't emphasize this enough. Look at the first four postulates. Can you draw 2 points, given 2 points, can you draw a straight line between them? Postulate 1, is it satisfied? Can you fly directly from New York to London on what? Yes, you have to, because you and I would want to have a definition of what it means to be a line, but we must separate ourselves from our definition of straight line. You're absolutely right. We're not going to burrow through under the Atlantic Ocean to get there. But a straight line, if I get into an airplane and I lock the wheel straight and I fly along a geodesic, I will get from any point to any other point. I just have to angle it in the right way, right? I direct my plane the right way. I follow the straightest path I have access to on the surface of the sphere. That's postulate 1. Postulate 2, having already flown from New York to London, can I just keep flying a little farther if I keep my plane going straight, right? I can keep going. I can extend any given length. That's postulate 2. Postulate 3, is there a circle of equidistant, whatever the distance is from New York to London, can I fly to all of the other points that are the same distance as the distance from New York to London? No problem. Postulate 3 is true. Right angles, are right angles the same between north and east here as opposed to between north and east there? All right angles are the same. The first 4 postulates are just as valid in spherical geometry as they are in Euclidean geometry. And yet let's look at the construction we just proposed. Okay, I'm going to start over here on the equator. Let's say I have some distance. So this is A and B. I'm going to drop a perpendicular. And I'll move the length of, and I'll drop a circle. I can draw circles. So whatever this length is, I'll make that length the same. What do we call that point? D. Okay, so this length is the same as that length. Then I'll drop another perpendicular here. Drop another perpendicular here to a point G, I believe, and make this length equal to the other length. And you see the problem. The thing that I said, I can connect B and G. There's no problem connecting B and G with the geodesic, with the shortest path. We will not be able to prove that this makes a square because it doesn't make a square. This will not be a right angle, that will not be a right angle, and that distance will not be the same as the other distances. It's very, very subtle. And it's so, pictures can be deceiving. This is the point that I've been trying to make since our failure of proposition 1, failure to prove rigorously proposition 1, is that pictures can be deceiving. And the fact that this construction, that this simpler construction does work, doesn't mean that it's easy to prove. It's actually much, much harder from this construction to prove that what you've constructed in Euclidean space is indeed a square, because you have to really be able to separate that situation from this one. Whereas what Euclid does is very smart. He goes straight to parallels. Once he's made that first perpendicular, then he uses parallel here, parallel there. And then it's one, just a few more steps to get that what you've constructed really is a square. I'm going to emphasize that point. Okay, does that make sense? All right. Let's do I-47. I don't know if we can prove it in 10 minutes. I think we can. What do you think? We're up for it, right? I-47, drum roll, please. We all know what I-47 is going to be. We already discussed it last time. The Pythagorean theorem. Let's set it up at least if we can't give the full proof. Okay. Proposition I-47, the famous Pythagorean theorem. If, let's write it in words, in a right triangle, the sum of the squares on the sides is equal to the square on the hypotenuse, is how he would say it. Or he wouldn't even use hypotenuse, he would say the largest side. How do you sum squares? Sums implicitly means area. Implicitly means area. Okay, so again, if you just read it, in a right angle triangle, or in right angle triangles, but I think it's better to say in a right angle triangle, the square on the side opposite the right angle equals, in area, equals the sum of the areas of the squares on the sides containing the right angle, that are adjacent to the right angle. Okay? This is the famous windmill proof. So this is called the windmill proof by some people, because it looks a little like a windmill. He imagines should I try to keep, you guys are bothered when letters change. Let me try to keep the same letters as in his picture. Okay, so A is going to be the right angle. A is the right angle. B is over here, C is over here. And I'll make that the right angle. Okay, so we're given triangle ABC and angle CAB is equal to, whoops, angle CAB is equal to a right angle. That's our assumption. Step 1. So this is step 0. Step 1, construct squares on all sides. Bless you. Why are you allowed to construct squares? I-46, we just did it. That's the first thing that he needs is I-46. So I'm going to construct a square on here. I'm going to construct a square on here. And I'm going to construct a square on here. And let me keep the letters the same as the letters in the diagram again, since you guys like that kind of thing. Okay, so we'll put FG over here, FG over here. We'll put DE down there. And these two are H and K. Okay. Next step is to draw a perpendicular. I'm going to drop a perpendicular to DE through A. Draw a perpendicular to DE through A. Why can we draw perpendiculars? This is I-11 or something. I-11-ish. And let's give this point a name. L. Curiously, he doesn't give this point a name. I think it's useful to have a name there. What do I not? K, L, G, M. How about M? Okay. And the claim, the reason he's drawing this is really, really, so you see why it looks like why it's called a windmill proof. Here's the claim, is that the area of the square ABFG is equal to the area of the rectangle MLDB. MLDB. This area, he claims, is equal to that area. And the same argument will tell us that that area is equal to this area. So he's explicitly showing you how the bigger square is the sum of the two smaller squares in area. Okay, cool. Yeah, in the interest of time, I won't draw this in GeoGebra. Actually, it doesn't take that long. Why? Why is this true? Okay. Here's his argument. This is beautiful. Step 3 is to draw CF. So I'm going to draw from C to F, straight line, and I'm going to draw AD. AD, a straight line, and AD. Why am I allowed to draw straight lines? P1. The first thing you do is you draw straight lines between 2 points. Okay. Now, there's a theorem. I think it's called I-41. I-41, let me have a little aside over here, is that if you have two parallel lines and you have a parallelogram between those two parallel lines, if this is a parallelogram, or you have a triangle with the same base as the parallelogram, okay, area of the parallelogram is twice the area of the triangle. This is I-41. Where was it? 41. Okay, whenever you have a parallelogram, the area in the parallelogram is twice the area of any triangle as long as they lie between the same two parallelograms and have the same base. You trust me on that statement? We don't need to prove that statement. Here's his claim. His claim is, let's look at the triangle. Before that, my claim is that CBF, this triangle, CBF, let's color this in. Triangle CBF, I claim, is congruent to triangle ABD. That's the claim. Claim is the triangle, not angle, triangle CBF is congruent to triangle. Okay, I have to be a little careful. C is the same as D. B is the same as B. And F is the same as A. All right. We're going to prove this by side angle side. Apply side angle side. First of all, I claim that BF is the same as AB. So BF is the same as AB. AB is equal to BF. Why? Zoom out a little so we can see everything. It's a square. It's a square. That's the same as that because they're a square. Because of a square. I also claim that BC is the same as BD. BC is the same as BD. BC is the same as BD. Why? Square. And then I claim that the angle in between them, this angle, is the same. Let me make this angle in red. This angle in red is the same as this angle in green. Why? Lori. Yes, exactly right. This is 90 plus this little angle, and this one is 90 plus the same angle. Let me go a little slower. Let me go a little slower. So this is angle CBF. Angle CBF is equal to angle CBF. That's actually the same order as the triangle. It's the same as angle DBA. DBA. Both are 90 degrees plus the angle at B, ABC, plus angle ABC. How crazy is that? So these two triangles are actually the same triangle. And then we're done. The red triangle is half of the area. Twice the area of the red triangle is the area of this square. Twice the area of the green triangle is the area of this rectangle by I-41. So the square and the rectangle have the same area. We'll do this again next time a little bit more slowly, but we finished the proof. We'll do it again and we'll go on from there.